Hello, this is Akira Oiwa. I'm a professor in Osaka University and I'm working on semiconductor quantum technologies in nanoscale. On 9th November of 1989, I was a high school student. Although I was very busy in the preparation for the entrance exam for the universities at the time, I remember that the Berlin Wall falling was a big issue, also in Japan, widely reported on the TV. Because a cousin of my mother lived in Germany at the time, I had some familiarity with Germany and wanted to study science and play football in future in Germany. Although it was an event happening in a distant country for me, it was enough to make me feel the atmosphere that something was changing in the world. When I was in elementary school, I participated in the excavation of archaeological sites. Probably I wanted to become an archaeologist for the Asian period of Japan. I was fascinated very much by the freedom to create stories by discovering and deducing what were known in the literature. In my high school period, two things attracted me: football and high-temperature superconductivity. The cutting-edge and amazing results made me dream about the new technologies and future societies. Unfortunately, I couldn't have a chance to study the high-temperature superconductivity during my graduate course. Instead, I could meet the semiconductor quantum devices. Information is becoming more and more important in our daily lives. At the same time, the quality and quantity of information will change drastically, and I believe that its correct and appropriate use will lead us to a wealthy and safe society in future. One of the technologies to realize such a future is quantum technology. While the information is conventionally expressed by 0 and 1, the superposition of 0 and 1, which is one of the quantum mechanical properties, can be used as an information carrier. We try to develop the hardware that are the building block of a future information processing network that is quantum internet toward an absolutely secure communication and advanced information processing utilizing quantum mechanical properties. Currently, we are working on a project to develop an interface that converts the quantum information between photons and electron spin in semiconductor quantum dot. Our recent innovation is a transfer of quantum state between a single photon, which is the basis of quantum communication, and a single electron spin, which is a promising qubit for the quantum computing. We have demonstrated that a photon polarization which brings information as angular momentum is observed in a quantum dot and is converted and can be detected based on the power exclusion principle. This achievement will enable us to connect the quantum computer to a quantum network, providing information processing not possible for conventional computers. I believe that my research will contribute to creating an advanced society where the personal privacy is firmly protected by absolutely secure information processing. The transfer of quantum information from a single photon to single electron spin has almost been completed. Early demonstration of a conversion of entanglement, which is a superposition of two physical systems from photon pair to the electron spin pair, is key technology determining whether the spin qubit using the semiconductor quantum dot can contribute to quantum internet in the future or not. In recent years, the competition in realizing quantum internet has intensified among various quantum systems, such as light, ions, atoms, superconducting qubit, and diamonds. Although my wife, my children, my mother may not fully understand what I'm studying, they always encouraging and helping me a lot.